My name is Mark Murphy. I'm from Commonsware. You may know me from 13,000 and some odd answers out on Stack Overflow and various other crazy things I seem to do. And today, I'm here to talk to you about memory. Yes, I'm here to talk to you about memory. And don't worry, the jokes get better and better all the time. Quick logistical item, and that I'm not sure whether Samsung is publishing the slides or not, but if you follow me on Twitter, I'm Commons Guy there, I will tweet out links to be able to get to these slides, and that either later today or tomorrow. So don't feel you need to take camera shots and that all along the way, though you are certainly welcome to do so if you are so inclined. Quick show of hands, how many of you do not write Android applications? Those of you who raised your hands, you'll notice the little green guy there in the corner. This is a relatively technical presentation on Android application development, and that's specifically related to memory management. And so some aspects of this may be a little tough to follow. For the rest of you, who therefore presumably do write Android applications, raise your hands if you've ever gotten an out-of-memory error. Oh yeah, and that out-of-memory errors are fun, and that we run into them with great frequency in Android, and that's really what the core of this presentation is about, is trying to deal with those sorts of things. And that the key first tip is to understand really what's going on when we get those out-of-memory errors. If you are getting an out-of-memory error on a single large allocation, which the vast majority of the time means you are loading some bitmap, you're probably not actually out of memory. Out-of-memory error is a very literal error message on Java. It is less literal in Dalvik. Your problem is that your heap is fragmented, that there is no single contiguous block of space that is available for the particular allocation that you're doing at that point in time. And that's because Dalvik does not have a moving or compacting garbage collector. Let's imagine we've got a heap. We allocate 3 objects on that heap. We then allow 2 of those to be garbage collected. We let go of our references to them. While they were originally 2 individual blocks, a moving or compacting garbage collector, like the Java VM has, will coalesce those into one larger block. And so therefore, we can allocate space up to the size of what A plus B had been before. But let's suppose instead we held on to B, and we were letting A and C go through and get garbage collected. On Java, we would move B around, slide it to one end or the other so we could coalesce the free space again. On Dalvik, it does not do that. It is a non-compacting garbage collector. And so therefore, we cannot actually allocate enough space. We can't even do what we did before. We can't allocate A plus B because all we have are A and C are each smaller than B, A plus B. And so even though we have more free memory here, you ask, runtime for the amount of free heap space or something like that, it's going to say we have more memory. We don't have a single big contiguous block for dealing with those bitmaps. And that's why you're getting your out-of-memory errors. You've got memory, you just don't have enough memory in one area for that allocation. Whereas if you get an out-of-memory error on pretty much anything else, garden variety objects, okay, yeah, now you really are out of memory. And that we have exhausted our heap entirely, and then you're in a world of hurt. And the rest of this presentation is a lot about dealing with that world of hurt. Now, no doubt many of you have seen the movie Apollo 13. You'll remember the scene where the CO2 scrubbers have become saturated. They need to grab the scrubbers out of the lander module. But they weren't designed to go inside of the actual, re-entry capsule and so forth. And so as a result, you've got the army of engineers, and that they lay out this ton of equipment and that on a table much like this, and they hold up the 2 CO2 scrubbers and that, the one from the module, the one from the lander. So we need to make this fit into the hole made for this using nothing but that. And that's effectively what we wind up having to do in our mobile development, and particularly on Android. That it's not like we can go in and ask the users, hey, could you pop open the back cover of your phone and solder in some more RAM? That'd be really cool. But we can't do that. This is a fixed environment. We have no great way of causing that environment to change other than maybe hinting that they ought to buy that, that really sexy new Samsung phone that just came out, because that probably has more RAM than what they've got right now. Our job is to figure out how to cope with the environment that we have, not pine for the environment that we don't. So, tip number 2. Design for low RAM. You gotta take this into account. It's a fundamental limitation, no different than the fact that, gee, that screen size on that phone's a whole lot smaller than that thing up there, and that you gotta take those things into account as well. The designers are not going to be super happy about the fact that we have low RAM, because a lot of the fancy, cool stuff that we want to do sometimes tends to be memory intensive. And therefore, we're going to have to be able to make the trade-offs. We're going to have to come up with designs that can avoid the huge scrolling lists. I get the questions out on Stack Overflow a lot. Yeah, I want to have this list view with like 10,000 rows in it. And it's like, ignoring all of the memory and every other stuff, do you really expect your users to fling through 10,000 entries in a list view? They'll get a blister. Come up with a UI that avoids that. Focus more on searches. Focus more on categories. Focus more on filtering, something to allow you to not only be able to present a more effective UI to the user, but one that can take less RAM in the first place. Figure out what is the ideal user interface, and then adapt it to figure out, okay, how can we shoehorn that into a relatively modest amount of memory? But it gets worse. Not all Android devices are created equal. Older devices are older, and frequently they have less RAM. Even new devices, you cannot assume that, oh, gee, I'm running on Android 4.4, therefore I must have a ton of RAM, because of things like Project Svelte that came out with KitKat, and that where they aim to get Android to be able to run in lower system RAM for initiatives like Android One, for emerging markets and so forth, trying to reduce the cost of goods and that the bill of materials for building up an Android device. You can run in as little as 512 meg of system RAM. That's going to have impacts on us. We'll not have a ton of heap space on those particular devices as a result. And so we're going to have to do some of the same sorts of things you do in web development, graceful degradation and or progressive enhancement, depending upon what direction you want to look and whether you're one of those glass half full or glass half empty sorts of people. I tend to be the glass just spilled all over my shoes sort of person, but that's a whole other story. And so come up with plans for, okay, well, in the ideal world, we'll do X, but if we're on a very constrained environment for whatever reason, we're going to do this lighter weight thing. Maps is one example. In an ideal world, your designers would love to have the users who need to go view the map stay within your own application. Even if you're not planning on doing a lot of stuff with the map itself, in terms of drawing on top of it, just from a flow standpoint, they want to keep the users in the app, whether it's just from a navigation standpoint or because, gee, you can't show ad banners if it's not your app. And that'll be maybe okay on relatively hefty devices, but on lower devices, the additional memory involved with integrating something like Maps v2, that may push you over your memory budget. And you got to make the decision, okay, well, is it worth it to keep them in our app for this map when we could just go off and fire an action view intent to go bring up built-in mapping application? Yeah, that leads them out of our app, but gee, it's free, more or less, from a memory standpoint. And so therefore, maybe you compromise. You say, given that we have X amount of memory, we will keep it in our world, or if it is less than that amount of memory, and that we will lead the user into another application. But those are strategic things. A lot of what we wind up having to do here is a lot more tactical. It's a lot more in terms of architectural decisions, all the way down to lower level debugging. And a lot of that lower level debugging for making sense of our memory circumstances is going to require us to grok our heap. How much heap are we using? How much heap do we have? There's methods like getMemoryClass on Activity Manager that will tell you your maximum heap size that you'll be able to grow to. Could be as low as 16 meg, though nowadays something in the 24 to 48 range will be far more common. But you're then going to need to figure out, okay, what am I using that heap for? What stuff is floating around in that heap, given the fact that the user has gone through and has now spent X amount of time in the app doing all sorts of cool things? Or if it's not the user, maybe the test monkey has gone through and has randomly done a bunch of cool stuff inside of the app, or at least stuff the monkey thought was cool. And where's our heap going? How much heap do we have left? Where is that heap being applied to, and is it an effective way of applying that heap? And for that, you're going to want to turn to the memory analysis tool, aka MAT. And that this is a utility from the Eclipse Foundation, available as a standalone tool or as a plug-in for Eclipse, for those of you still using Eclipse. You can generate so-called heap dumps, either directly from DDMS from your preferred IDE to be able to say, I want to collect a heap dump now, or programmatically. There's a dump hprof data method on the android.os.debug class, where you can go say, maybe from some unit test that's giving you grief, I want to generate a heap dump after this test has been completed. Those heap dumps are basically a catalog of all of the objects that are floating around in your heap, minus those that would be garbage collected had we gone through and done a fairly comprehensive garbage collection. And therefore, you're going to be able to look through these results, figure out what's all going on in there, and be able to make sense of what's happening, understand, okay, what objects are being held on to for a long period of time. In particular, what are garbage collection routes? What are the things that are keeping all this stuff around? Now, a lot of the stuff that's going to be floating around in your heap has nothing to do with your app specifically. It's stuff that Android needs, and that resources and so forth that get loaded up as you use widgets and so on. But there's going to be a lot of stuff of your own. All those static data members, they're intentional memory leaks. And therefore, everything that they hold on to is going to be held on to strongly, can't get garbage collected. Threads. So long as those threads are running, not only can they not get garbage collected, but anything they could possibly get their hands on, virtually speaking, can't get garbage collected. Therefore, also your services, and that content providers, other components that are long-lived within your process, they aren't going to get garbage collected in the case of services while they're running. In the case of content providers, so long as your process is around, they won't get garbage collected. Anything that they hold on to means that that memory can't get freed up. And so you need to figure out, okay, what are they holding on to? Was I expecting them to hold on to that? Is it a good idea for them to hold on to that? Can I stop them from holding on to that stuff? And one key way of doing this is to basically try to find things that clearly shouldn't be there. If the user has back-buttoned their way completely out of your activities, gone back to the home screen or whatever, and so therefore you've got no more running activities in your process, and you run a heap dump and you see instances of your activities still floating around the heap, that's bad. Because they should have all gone away as part of the effective garbage collection that occurs at the point in time of the heap dump. And therefore, if the activities are still being reported there, somebody's keeping them around. Conceivably, due to the timing of the heap dump, it could be Android, but more often than not, it's something of your own. You did something that maybe isn't the best move, and therefore you use the punctuation that I have there in that bottom bullet. If we could switch to my notebook, please. You're looking live at Android Studio in my Linux notebook, and you're looking at an activity that is doing something that you shouldn't do. as evidenced by the fact that I have a data member named do not do this please. It's a static data member where in onCreate of this activity, I am grabbing a widget out of the layout that I am inflating and I am putting it in that static data member. In this case, that's completely stupid. I don't have anything else in this activity. There's no reason to have this be a static data member. But you may be tempted to do this. You may say, oh, I'm writing the chat application. I really want to be able to have this service that's got the socket on the thread going to the chat server. I want to be able, when messages come in, to be able to update my chat transcript. Oh, I'll just take my chat transcript widget and I'll stuff that in a static data member so my service can go get at it. Don't do it. Because you're going to possibly introduce a memory leak. So, for example, if I run this application, on my emulator, from a UI standpoint, it is, of course, complete noise. But then I'm going to back button my way out of that. And so at this point in time, I have no running activities in that particular process. But now I want to prove that. I want to confirm that I don't have anything unexpected in that process. If you were using Eclipse and you went and you downloaded Mat as a plugin for Eclipse, and that's from eclipse.org/Mat, you'll be able to, from DDMS in Eclipse, click a little icon, if I remember correctly, it looks like a can with a downward pointing arrow, and that to say I want to capture a heap dump, and will automatically go and load it up into Mat for your use. Android Studio's integration isn't quite that tight, in large part because Android Studio is not itself based on Eclipse. You'll have to use the standalone edition of Mat, also available from eclipse.org. But you're still going to go find your process, in my case, Commons or Android tuning Mat, and from your toolbar, choose the dump Java heap, which has an icon that I frankly don't completely understand. But if I tap that toolbar button and I wait a few moments, because this takes an astonishing period of time, you'll get a little dialog where you can say that you want to save the heap dump somewhere, such as in heap dump, assuming I can type today. You'll want to leave this convert to standard HProf format checkbox checked. There's a couple of different ways the heap dump could be generated on Android. You want the standard one that Mat is then going to be able to go read in. Mat is going to then be able to give you an open heap dump option, where you can go in and load up that HProf file that you just created. Now, I could spend a half-day workshop just talking through Mat. We don't have that kind of time. And so this particular pie chart, is in Java realm is going to be useful, but most of the things that are reported in here are stuff that comes just from standard Android, and therefore is not really something you're at fault for. But if you go in and bring up something like the Dominator tree, assuming my Mat feels like behaving for me today, gotta love live demos. If I bring up my Dominator tree, did I ever mention my last name is Murphy? Well, if we pretended that I brought up Dominator tree, and that would give me a list of the largest objects that are outstanding, and that we'd have this table in there. There'd be a field in the top row of that table named regex. You can fill in like your package name of your Android applications, and be able to find all of the classes from that package that are still floating around in the heap. And if I were actually capable of bringing that up right now, and that I would go in and search for my particular application's package, we'd see that that activity is still being held on to. And I'd turn around and be able to right-click over the activity, say, show me the path to the GC roots. Who's holding on to this? And we'd see a series of data members that eventually lead back to that static data member of my widget, because widgets know the activities that they are that they are a part of. And so by putting the widget inside the static data member, the activity cannot get garbage collected even after it's been destroyed. And trust me, this normally works. It worked in the hotel room, and that maybe it's a Moscone thing. I don't know. But we'll have to abandon that demo. So if we could switch back to the slides, please. Now, finding out through tools like MAT what are you perhaps holding on to is kind of reactionary. The horse has left the barn. We are trying to convince the horse, hey, that's a really cool barn over there. Would you mind getting back in there? The better option in many respects is to try to minimize what you're allocating in the first place. We, of course, want to have all sorts of data available in objects in memory because they're easy. They're right there. We don't have to worry about background threads for getting them off of disk or getting them off of network. We did that before, and they're still floating around in our caches and whatever, and so that's all really cool. But we have this tendency sometimes to go load in way too much data. You go in and you query the table, and lo and behold, there's 10,000 items in the table, and so you now have this cursor that's the size of Mount Rushmore, and so forth. You need to figure out how can you load in the right data, not all of the data, because you don't necessarily have memory for all of the data, and even if you do right now, that may have then lingering issues over time for your ability to do allocations later on. Remember, we don't have a compacting garbage collector, as I talked about at the top. And so memory allocations not only have a penalty right now, but to the extent that they continue to fragment your heap, they are going to have penalties over time. Of course, our big problem with the memory, as we talked about earlier, is our bitmaps. They are the single biggest objects that we tend to allocate. The byte arrays, that's the backing data for those bitmaps, can be big, particularly if there's something like photographs. You may therefore be tempted to say, oh, okay, well, I'm just going to load up these images and we'll call it good. But, you don't have room for a lot of huge bitmaps in memory. You're better off trying to determine, okay, for this particular use of these bitmaps, what can I get away with? For example, list view rows. Same thing for grid view, recycler view, if you've ever figured out how to make that thing work, and so on. And we've got relatively small renditions of the imagery, even if they're backed by megapixel-sized photos, and that the user isn't seeing megapixels worth of data because they're being rendered pretty darn small. For that, you may want to consider using in sample size, field available on the Bitmap Factory options object that you can pass in when you're loading in bitmaps from Bitmap Factory, whether that's from disk, whether that's from some sort of a stream, whatever. In sample size says, don't grab every pixel, but grab every second pixel, or every fourth pixel, or every eighth pixel, or whatever. Has to be a power of 2. So it's going to subsample that image. And therefore, the amount of memory you're going to wind up consuming for the image in the end is going to be some fraction of the original size of the bitmap. Yet, because it's not just literally grabbing every eighth pixel, but it's doing a more intelligent analysis of the pixels as they read them in, you still can wind up with fairly reasonable sorts of looks depending upon the nature of the imagery you're loading in. If we could switch back to my notebook, please. So if I go back to my emulator and I bring up a sample and I get out of MAT, since that didn't do me a lick of good, I have a sample application where I have a view pager. It's loading up a bitmap fragment for each one of its pages, where I want to demonstrate the impacts of in sample size. And so for each one of these fragment instances, I'm going to be loading in a pair of images out of assets, so I make sure that they're not going to be automatically scaled or anything due to density conversions the way drawable resources might be. They're more akin to regular files. And my load method, I am going in and I am saying, okay, I want to say that I want to downsample those images. I'm passing in a sample size that, among other things, is going to be used as part of the rest of the UI of the view pager to say, this is how we have downsampled the image. And I use that in sample size in the bitmap factory options that I am providing to my decode stream method on bitmap factory when I go load these things out of assets. With an in sample size of 1, which says, give me every pixel, my purple flower is awesome looking. The Commonsware logo, pretty darn decent, but those are the full-size renditions of them. Those are how big those images actually are in terms of their size on disk. If I show them in a smaller rendition, 128 by 128 dips, and you see that, of course, they get shrunk down physically. And Android's built-in scaling, for the photos, not too bad. For the Commonsware line art, not so hot. But each one of those images is taking nearly 2 mega heap space. That's a lot of heap space for a flower, let alone some logo from some balding guy. But if I go with an in-sample size of 8, saying that I want basically 1/8 the pixels in the horizontal, 1/8 the pixels in the vertical, so 1/64 of the pixels overall, my memory footprint is now about 30K, a little less than that, closer to 25K. Yeah, at full rendition, the flower is fuzzy and the logo is yeah. But in the smaller rendition for the list view, that flower is still very recognizable as a flower. The Commonsware logo, yeah, okay. And so that's where knowing your data is going to come into play. If you know that your avatars are going to tend to be dominated by photos, or whatever it is that you're loading into these list views, then saying, okay, let's take a more aggressive in sample size, because that seems to be working fairly good. We get reasonable quality output, and we've got teeny-weeny memory impacts. But if you think that a healthy percentage of those may be some form of line art, and in your experiments, going very aggressive on the in-sample size means that you wind up with some output that isn't very aesthetically pleasing, okay, well, maybe you backpedal a little bit on the in-sample size. Try to make the trade-off between quality of output and the amount of memory you're consuming for these bitmaps, while taking into account the types of data you're loading in and therefore how aggressive you can get. We switch back to the slides, please. You can also consider loading in at different bit depths. By default, when we're loading in all of our bitmaps, they're coming in ARGB 8888, 4 bytes per pixel. You do have an option, though, with bitmap factory options to say that I want to, and I've got a typo on this slide, that's RGB, not RBG. The RGB 565, and that is your color space, which is now 2 bytes per pixel. So we're going to consume half the memory, even if we keep the resolution the same. Now, you don't have transparency anymore because we lost our alpha channel, and we don't have quite as much color depth on the images. Once again, though, you can run tests, see what this looks like against your real-world sorts of data, and be able to determine, oh yeah, again, for these little images that we've got in our list views or grid views or whatever, where we got a whole bunch of those images, not only can we use in sample size, but we can use a different color space to reduce the amount of memory each one of those bitmaps is going to take up. As I mentioned earlier in the discussion of MAT, the point behind MAT is to help you, fix your leaks, but in an ideal world, you want to avoid the leaks in the first place, where a leak in a garbage collected environment like Java is unintended retained data. Retained meaning it can't get garbage collected. Something like a static data member or a thread is preventing the garbage collection. And unintended, you weren't exactly expecting that stuff to be held onto. Or you were expecting it to be held onto, but you hadn't really thought through how much it was going to wind up being in the fullness of time. All else being equal, lean in the direction of existing frameworks, existing libraries for common operations like image fetching and loading, and that your object relational mapping engines, event buses, versus rolling something yourselves. There's a disturbing number of people out on Stack Overflow and that who say, well, I'm trying to avoid third-party libraries. And it's like, for the love of deity, why? They wrote it. They tested it, we think. And that they documented it, maybe. And that it usually beats the heck out of you doing all that stuff. And in particular, when it comes to memory management, assuming that those libraries have already been beaten up, probably other people have gone through and experienced the pain of the memory management of those libraries, and therefore a lot of that stuff was hopefully fixed or more documented in terms of the proper use patterns for it to avoid memory problems and so on. Beware the application. The application singleton context, you get it from calling like get application on your any sort of other context, that is a singleton context created when your process is. That's got ramifications. Some developers, are fond of subclassing that, saying in their manifest, oh, don't use android.app.application, use my application class, which is cool. I'm not convinced that that's necessarily an improvement over static data members, but there may be some benefits there. But again, it's global in scope. It's static. And whatever it holds on to can't get garbage collected. Conversely, there's going to be cases where you specifically want to use the application context. If you legitimately have something that you want to be storing in some sort of a static environment, and it may have a context associated with it, all else being equal, you want to use the application context for that because it's already leaked. You can't leak it more by somehow having more references to it. So for example, I'm the author of the Wakeful Intent service, and that think Wakeful Broadcast Receiver before Google actually implementing that. And I need to hold a wake lock in order to be able to allow your alarm manager or job scheduler, well, actually job scheduler doesn't need it, but alarm manager or, GCM message or whatever that comes in, you want to keep the device awake long enough to get some work done, I'm going to hold on to a wake lock for you. And getting a wake lock does involve a context. As far as I know, it's not holding on to a reference to that context, but who knows? Those rules of the game may change later. And so therefore, I specifically make sure that I get that wake lock by means of the application context, so that if today or tomorrow there's a reference in that wake lock object to the context that created it, that I don't wind up leaking some service or some broadcast receiver context passed into the onReceive method or whatever, and that I don't have to worry about accidentally leaking something more. The QR code there is for a blog post by Dave Smith, and that named Context? What context? And that's a brilliant post, and that describing various sorts of contexts in Android, when to use which ones, including when to use the application context. Make sure that you're understanding the lifetimes of your threads. Everything your threads can get to cannot get garbage collected. And so don't just fork a thread and kind of forget about it. Besides all of the CPU ramifications and so forth, you've got memory impacts from that as well. To the extent you're maintaining some sort of a thread pool, make sure that the thread objects themselves don't hold on to things that we're going to hang around in that pool by virtue of the threads themselves hanging around in that pool. The everlasting service anti-pattern. I'm going to start up this service and I'm going to have it run forever. That's got loads of issues, not the least of which is from a memory standpoint, and that service and its threads and everything they can reach can't ever get garbage collected while that service is running. Only have services running when they are actively delivering value to the user. In particular, watching the clock tick is not actively delivering value to the user. Use Alarm Manager, Job Scheduler, something, and that for those sorts of periodic bits of work. You're going to want to maintain caches of stuff. You are going through CPU and bandwidth expenses for loading in stuff from disks and networks and so forth. But you don't want to have caches that are unbounded. They are just going to grow and grow and grow and grow and grow because eventually they're going to get too big. That getMemory class method that I mentioned on Activity Manager will give you an idea of how much heap space you can grow to, and you can use that as a basis of algorithms for saying, okay, I'm going to scale my caches based upon my possible heap. I am willing to allow this cache of Pojos to take up 10% of my total heap. This cache of bitmaps I'm willing to allow to take up to 20% of my possible heap, and so forth. On top of using things like weak and soft references, so that to the extent that Android still needs that memory, and that from a garbage collection standpoint that it can be retrieved, but so that you're not holding on to it too much in the first place. Because if nothing else, if we have to get to the point of reclaiming weak and soft references, that's tending to be slower GC operations, and that ones that may, have more stutter in your UI as it freezes a moment while we are going in and doing the GC pause. And while I recommend using third-party libraries, make sure that they are, if they are doing caching on your behalf, that they are exposing controls so that you can size those caches. I mean, if every library thinks that they're the special snowflake and they can use up half of your heap, and you've got 5 such libraries, that math don't work. And that you're going to need to be able to go in and tell them, no, while half of my heap might be, well, okay, maybe that's not a reasonable default, but yeah, it's the default that they coded in there. We want to specifically say that we want to have this take up much less of that available heap. If you are maintaining your own caches, or the libraries give options for you to be able to go in and hint to them, hey, could you please tighten your belt a bit? One key place to do that is the OutOfMemory method. This is going to be called on lots of things, your activities, services, content providers, that application singleton, and so forth. This is going to be called at various points in time in the operation of your process, letting you know what's going on in the outside world and what impacts that's going to have on your process. In particular, these are times when it's suggesting that you ought to trim some of your memory, release heap space. Not only is that good for your own process, but Dalvik will actually return memory to the operating system. If you happen to allow enough garbage to be collected that some page it had allocated from the kernel is totally free, and there's enough other free memory around, Dalvik will actually release that memory back to the OS. And therefore, that's going to reduce the size of your process, how much memory your process is taking up. Smaller processes tend to live longer than do larger processes. If Android's got to terminate a process to free up memory, all else being equal, they'll tend to pick on the one that's bigger, more bang for the buck. And so to the extent that you can reduce your memory footprint, not only will that maybe help from future garbage collection and memory allocation work, but also being able to go in and keep your process small. The trim memory running flags, if you get one of those passed into on-trim memory, that says your process is in the foreground, you ain't going anywhere, but hey, outside of you, life is getting increasingly bad, and therefore to the extent that you can go in and free up some memory that might therefore allow memory to be returned to Android, that'd be good. Once you start moving towards the background, though, now you're at risk of your process being terminated. And so not only are you freeing up memory in order to give you more heap space, but also you're going to be hopefully reducing your process size and therefore trying to stay around a smidge longer. Bear in mind, though, that on-trim memory is new to API level 14. If nobody else at a previous conference or event that you have attended has already done so, you are hereby authorized to set min SDK version to 15, as far as I'm concerned. But if you are still supporting older than API level 14, bear in mind that these 3 scenarios, you're in the background and memory is getting increasingly tight. You are rising up the list of processes to be terminated due to low memory. That's available as the on low memory callback on those older devices, and that available on many of the same objects as I mentioned. One way to reduce the amount of memory allocations you do is to reduce the churn, and that you maintain object pools. that when you allocate things, you don't necessarily then let them get garbage collected, but you reuse the objects for later purposes. And that you say, okay, I'm going to have such and so many objects at the outset. Maybe I'll grow the pool based upon need. Maybe I'll allow the pool to then shrink back down to some minimum size. But that you keep a number of those objects around and reuse them. It is more efficient in many respects to reuse the existing instances than it is to have those be garbage collected only to reallocate those same sorts of objects again later on. This, in addition to perhaps reducing the amount of churn that's going on, is going to reduce your heap fragmentation. And that it's one of the few things we can do that controls heap fragmentation. And that if you keep reusing some of the same objects, we're not going to be constantly doing allocates and frees, and therefore possibly splitting up larger hunks of memory, and that is part of giving us a small hunk of memory. And, it saves on CPU time in terms of constructor invocations, garbage collection work, and so on. But of course, the whole point behind garbage collection was to get away from this stuff. And so we're kind of back into a malloc and free sort of scenario where we have to keep track of the objects ourselves, make sure we return them to the object pools and so forth as needed. You'll see a lot of this stuff in Android proper. Sensor events, and that, for example, and that as soon as the sensor, the on-sensor changed callback returns, you can't rely on using that sensor event object anymore because it's automatically going to get recycled by Android for a future sensor event. You have to make sure you copy your data out of there. For your bitmaps, the in-bitmap parameter on bitmap factory options says, here is an existing bitmap object that I had allocated previously. Please reuse this, if you can, for this new bitmap that we're loading in. This allows you to maintain an object pools of bitmaps, and that's particularly important for being able to make sure that you can successfully use those bitmaps. If you allocate a bunch of bitmaps, release them, and try allocating that same set again later on, you may not be able to because the heap got more fragmented from your original allocation to the later one. If you know you're going to be using those bitmaps memory again likely in the future, you may want to say, let's hold on to it and reuse it via in-bitmap. The biggest limitation is up until fairly recently, it had to be an exact size match. That the bitmap that you are trying to load in exactly fits the bitmap object that you're trying to reuse. API level 19, Android 4.4 and higher, and that we can say that if the bitmap we're trying to reuse is the same size or larger, we can reuse it, and therefore gives us a bit more flexibility. But for scenarios where your bitmaps are known to be a uniform size, it's the avatars that you're downloading from Twitter for the timeline and so forth, you know they're going to be a uniform size. In-bitmap is a great way of avoiding allocating fresh bitmaps all the time. We as Android developers have this tendency of wanting our processes to live and keep living. But it's many times in your best interest to allow your process to go away, because when your process comes back, boom, you got a nice clean heap again. No fragmentation to worry about. And so don't get caught up necessarily in the must keep process running sorts of scenarios, let your process go. Let it get terminated, and when you come back, yeah, you may have to do some more initialization work, but on the other hand, you got a clean heap, and that you're likely to be able to succeed with whatever allocations you need to do. But all of that may be insufficient. And so, in the worst case scenarios, cheat with integrity. Cheating, by that I mean we're going to do things that solve some of our heap concerns, though it's a whack-a-mole situation. We're going to solve one problem only to cause problems elsewhere. With integrity, I mean realize that this is cheating, that this isn't a long-term solution. This is the, gosh, we need to ship in 2 weeks sorts of solutions, and where you have a plan of being able to hopefully invest the time to avoid this so that you can clean up the problems that you are in turn creating. You can request a large heap in your application object. Android large heap equal true. Probably this is going to give you a large heap on newer Android devices, though there's no guarantee. and particularly on Android One style devices, and that you may not get any actual memory improvement. But if you do request a large heap, Get Large Memory class will tell you how much heap space you can grow to, and it can be substantially larger. But this is designed for apps that need a ton of RAM in one time, your image editors and video editors and so forth, and that this is not a solution for, gosh, I got this one random out of memory error and that quick large heap, and that because it means that your process is going to wind up growing to a larger size. Prior to large heap, we had to go with multiple processes. You'd arrange to have certain components of your app run in a separate process, and therefore be able to have 2 heaps, or conceivably more heaps than that. Even today, some developers will use this for a focused heap. They'll say, okay, well, I'm going to have this long-running service. I'm going to have that run in a separate process so that way the UI process can get terminated due to low memory conditions so that that memory can all get freed up because the service doesn't need all those activities and widgets and whatnot. That's cool, and that on-trim memory may allow you to avoid the overhead of the second process because it will add overhead, both in terms of actual system RAM consumed and in terms of the IPC that's going to intrinsically have to go on between those processes. If you're using the NDK, little known trick of the NDK is all those mallocs and frees you're doing there are coming from the OS. They're not coming from the Dalvik virtual machine, and therefore they do not count against your Dalvik heap limit. And so some people will move code into the NDK, do it in C and C++, maybe because they want the full power of native instructions, but also to get more memory. But all of these are going to cause your system RAM consumption to climb. You are getting away from the heap limits, but that RAM is still counted against your process. It's going to increase the odds that that process will eventually get terminated, and that due to low memory conditions. And as I mentioned, there's the additional overhead of the IPC, inter-process communication, and therefore adding CPU time and that to a lot of your communications. Try to keep the protocol between those processes coarse-grained. You might wonder if ART, the new runtime that came out with Android 5.0, improves things here. And if you read the documentation that was released at the time of Android 5.0 shipping, you would think that the answer was not really. The documentation was wrong. And that in particular, the moving garbage collector that Dalvik lacks is available in ART. When your process is in the background from a UI standpoint, it will go into a moving mode. It will shuffle objects around in memory in order to have larger contiguous free blocks, make it easier for you to allocate those bitmaps later on. In addition to having separate spaces in the heap for large objects like bitmaps that have few, if any, outbound references to other objects, makes it easier for them to reclaim those when garbage collections go on. And so in the fullness of time, ART is going to materially help, pun lightly intended, our ability to avoid out-of-memory errors, but of course it will take some time for ART to get around to all available users. And there's tons more. You could spend, lots of time on dealing with memory management issues and that ways of addressing them and so forth. And that again, I'll be publishing these slides later today or tomorrow. Follow me on Twitter. I'm Commons Guy there if you want to download the slides. We are real short on time, and so I won't have time for questions because we need to get you all upstairs. There is a technical keynote coming up here shortly. But I will be in office hours, and that I will be in the Hacker Lounge at 2 o'clock today if you've got questions you want to ask then. And that apologize, I had so much I wanted to tell you that I ran a little long, and so I'm not going to be able to take questions right now. So I thank you all for attending and enjoy the rest of the conference.